In the Pythagorean theorem and its converse, we're looking at one of the major theorems that we have in geometry. Now, the Pythagorean theorem says if we have a right triangle, then the sum of the lengths of the legs squared is equal to the length of the hypotenuse squared. Now, a lot of students want to jump to c squared equals a squared plus b squared, which is correct as long as c is the hypotenuse and a and b are the legs. What's more important is to remember that the hypotenuse squared is equal to the leg squared plus the other leg squared, and this always works in any right triangle. Now, sometimes we get nice sets of numbers that work for Pythagorean theorem, and we call these Pythagorean triples. And here's a couple of them right here, 3, 4, 5, 5, 12, 13, and 8, 15, 17, for example. These will always give you whole number solutions whenever we have Pythagorean theorem. They will also work for multiplying, if you do multiples of them. So if I did 3, 4, and 5, but instead doubled them and had 6, 8, 10, that would exist as a Pythagorean triple. 15, 20, and 25, if I multiplied by 5, anytime you multiply them up or scale them up, like similarity, you'll still have a set of numbers that work nicely for Pythagorean theorem. These are not the only ones, there's many others, but these are the ones we see most often. Then we get to the converse. The converse is if we switch the order of what's set up here. So instead of saying if you have a right triangle, then this exists, now we're saying, well, what if you had this statement? What do you get? And we get the first one, that if c squared is equal to a squared plus b squared, then it's a right triangle. Nothing really new there, it's a way we can test to have a right triangle. But what if c squared is less than? So what if we had not a hypotenuse, but a longest side, and it wasn't enough? It was less than, so it did not turn out to be equal to a squared plus b squared. Well, if we picture that, and we took this side here and shortened it, it would shorten it in and close in the triangle to give us an acute triangle. So anytime c squared is less than a squared plus b squared, we're going to get an acute triangle. Also think of it as less than, and an acute angle is less than 90 degrees. If c squared is greater than a squared plus b squared, c squared is too big, it's bigger than a squared plus b squared, it opens up the triangle and gives us an obtuse, which if we think of obtuse, angle is greater than 90. So we can relate it in that sense. And it's important in this, for the inequalities, that you put c squared, or the longest side, first, and then the inequalities hold up to match. And we'll look at those in a few minutes. But let's first focus on really solving with Pythagorean theorem. So I have a triangle, I have a base, I have a side length, and I want to find the height. So this comes from what we've done and spent a lot of time on in past units. This could be related to a perpendicular bisector by saying, since it's isosceles, this point is equidistant, it's on a perpendicular bisector. So we could put right angles and midpoints. It also could go back to looking at congruent triangles. By congruent triangles, we could show that these two triangles are congruent. Then you have corresponding parts, and what we really want here is that it's a midpoint that splits the bottom side of 22 to be 11, because now we get 24x and 11. So here we can solve with Pythagorean theorem. So longest side is by itself, that's our hypotenuse, 24 squared equals 11 squared plus x squared. 24 squared is 576. 11 squared is 121. We're going to subtract 576 minus 121, and we get 455 equals x squared. Now we take the square root of both sides, and we get the square root of 455. Now we have to look to see if we can simplify the radical here. 455 is, one of the factors we know is 5. And it's 5 times 91. Then, if we had 91, that is 7 times 13. So there's no pairs to pair up for that, so we're just going to leave it in simplified radical form as the square root of 455. But if we wanted the decimal, let's say it's asking it for the nearest tenth, we could say it's about 21.3 units. In the next problem, we have Kurt is building a rectangular deck. The dimensions we have are 10 feet by 23 feet, and we're looking at the diagonal. Now if it's a rectangle, we know we have right angles, and this becomes our right triangle with 10, 23, and x. So we're going to say x squared equals 10 squared plus 23 squared. x squared equals 100 plus 23 squared is 529. Then x squared equals 629. So we need to take the square root of that. Now, if we look at the square root of 629, it's not going to simplify down for us. So x equals the square root of 629. But that doesn't really make sense. If we're looking at the measurement of an actual object, Kurt's not going to look at his deck and say, oh, it's square root of 629 feet. So this is where we actually would use the decimal. The decimal approximation makes more sense in this case because it's an actual application problem. So we'd say it's about 25.1 feet. In our next problem, we're just solving for a missing side. Pay attention to which one is the hypotenuse and make sure you get the order set up correctly. X is the hypotenuse, so it goes by itself. X squared equals 8 squared plus 13 squared. So then we got x squared equals 64 plus 169. That comes out to be x squared equals 233, and x is the square root of 233. Now, can we simplify 233? It doesn't look like it. It's not going to have any sets of factors that come out, so that is what it is in simplified radical form, or as a decimal, it is about 15.3. For next one, 9 is the hypotenuse this time, so we're going to go 9 squared equals 7 squared plus x squared. That's 81 equals 49 plus x squared. We subtract 81 minus 49. We get 32 equals x squared, and x equals the square root of 32. This radical we can simplify, because 32 is 16 times 2, which gives you a set of 4s from the 16. So this becomes 4 root 2. That would also be about 5.7 if you wanted it as a decimal. Moving down, we have the hypotenuse is x, so x squared equals 22 squared plus 27 squared. So x squared equals 484 plus 729. So this gives us that x squared is 1,213. So that has 1,213 inside the radical. Okay, and that's not going to simplify as a radical, so we're just going to put that as about 34.8. Okay, so we went through and we did the Pythagorean Theorem. Now we're going to look at the converse. So in the converse, we have to set the longest side out in front by itself. 39 is the longest side, so 39 squared equals 31 squared plus 35 squared. Now we don't know if this is going to be equal, but we're just kind of putting that equal sign there as a placeholder to then see what the inequality is going to be. 39 squared is 1,521. 31 squared is 961, and 35 squared is 1,225. If I add 961 and 1,225, I get 2,186. So I have 1,521 and 2,186, which obviously it opens up. This is greater. If that is greater, that tells us that the longest side is not big enough. It is less than. So if it's less than, we want to think acute. So it's an acute triangle. For our next one, we have 9 as the longest side. 9 squared equals 3 squared plus 7 squared. 81 equals 9 plus 49, which gives us 81 and 58. So in this case, 81 is bigger than 58, clearly. So that means the longer side is greater than. The longer side is bigger than the other two. If it's greater than, we want to go with obtuse. Last one, we have 29 squared equals 20 squared plus 21 squared. 29 squared is 841. 20 squared is 400. and 21 squared is 441. If we combine the right-hand side, we have 841, and it's equal, so that's going to make it a right triangle because it is equal values where the longest side squared is equal to the sum of the other two sides squared.